Time for calculus. So those first three videos, those were just getting us used to parametric equations. Now let's do calculus with them. So we actually just did calculus in number 3, but it's hidden. In our third video, we found the slopes, right? We found the slope. That's just like going back to pre-calculus, algebra, stuff like that, where we don't need calculus to find the slope of a line. But what if they're slopes of curves? What if our parametric equations are defined by this blue line here? And we want to find the slope of the tangent line at that point. Now we need calculus. So let's jump into it. And our whole game is we want to know what's dy dx. We're going back to Calc 1. What's the slope of the frickin' tangent line for any value of x? But we're going to do it. What's the slope of the tangent line for any value of t? So hang on. Do your best. So we're going to say, right, our x is equal to some function of t. And we're going to say y is equal to some other function of t. Now, for us to get our dy dx, I actually want to solve for dy dt. Now, you don't have to understand this. Just do your best. Hang on. See if maybe something clicks. If it doesn't, don't worry. You're just responsible for the outcome of this. Now, wait a second. Wait a second. Isn't y needs an x? Hold on. Hold on. I think we have something here. If we were to mess with this and get this t out of there and we hit both sides of this and said f inverse of x is equal to t, and then we took it and we popped it in. Again, you don't have to understand all this. Oh my goodness. Oh my goodness. I'm writing in. This is in Newton's notation. But let's write this in Leibniz, where we're moving into. If you are a calculus student that has to go on to differential equations, you're going to be writing a lot of Leibniz. This is Leibniz. Hopefully you know those, and hopefully your teacher told you what those are. This is a chain. This is a chain. So when you do a chain rule, don't you have like g prime of... and then you leave the inside alone, and then you got to take a derivative on the inside? Well, what's going to end up happening here, I'm not going to continue on with this, we're just going to cross that out, is you're taking a derivative on y with respect to x first, because that's a function of x. But x is no longer just x. It's a function of t. So then we would actually multiply by dx dt. Again, you don't have to understand all this. I know I didn't. And we're trying to find dy dx. So what ends up happening is we divide this out, just like it's some multiplications. Right? Isn't that how we did it with chain rule? And we find out dy dx is indeed equal to dy dt over dx dt. And you're like, okay. But all that is saying, oops, I wrote f. It's the derivative on y with respect to t divided by the derivative on x with respect to t. Like a short way of putting this that your book's not going to show you is just say it's y prime over x prime. Our parametric equations. Now here's the general form. Derivative for parametric curves. Let x equal f of t, g equal, or y equal g of t, blah, blah, blah. They're differential on the interval. Well, it got to be an interval that they're differentiable on if you're going to take a derivative. Then the slope of the line tangent to the curve at the point corresponding to t is, yeah, the derivative, the slope of the frickin' curve. So we never have to actually find dy dx. We do it with t's. Well, you do find dy dx. You're just doing it without ever having to change into y's and x's. Now, again, I told you there is a beautiful visual proof if you want to check that one out, but I only have so much time to do so much in these videos. Let's do a problem. So what we want to do is take this, let's say x, I'm stealing this straight from your textbook. X is equal to f of t, right? That's our big thing. Now, let's just keep it mellow and just call it t. Let's call that t. All right, and then let's say y. We're going to call it some g of t, and let's call it 2 root t. And we say that we're only doing this for t greater than or equal to 0. So we want to do 2 things here. First off, we want to find dy dx. That's about as mellow as it gets. And then next, I want to know where... Actually, no, not where. Let's say when. What value of t? When t. When. And t doesn't have to be time, but it's fun to just use it because we understand time. When, not r, is, sorry, English not my strong suit. When is the curve horizontal or vertical? You know, horizontal when the slope of the tangent line is equal to 0, or vertical when dy dx might be undefined, but only in a special way, you know, dividing by 0. Okay, cool. Well, let's do this problem. And I don't even need much room. You just do it right in here. Our question is, what's dy dx? We're like, come on, bro, we got this. Dy dx. Well, that's just our g prime of t divided by our f prime of t. And oh my goodness, look at that f prime of t. That's going to be a rough one. How are we ever going to take a derivative on t? It's just 1. And now we're going to take a derivative on 2 root t's. You know, 2 times t to the 1/2 power. Let the 1/2 fall. You just get t to the negative 1/2. So that's equal to 1 over the square root of t. Cool. We found it. We found the derivative. That was super tough. No, it wasn't. It's pretty simple. Dy dx. So the work isn't super tough, but you got to know what everything means, and you got to know your formulas, right? So we just did part 1. So we found the slope of the tangent line for any value of t. So when I say when, I'm referring to t. Is the curve horizontal? Well, the only way the curve is going to be horizontal, let's try it. This is the way we'd find out. We'd be like, all right, when it's 0 over some number. All right, that's the only way something can equal 0. The numerator equals 0. But I'm pretty gosh darn certain 1 does not equal 0. You know what I mean? Pretty sure. So it's never horizontal. And we're not, notice, we're not graphing this. Let's say horizontal. Never. It's never horizontal. What about vertical? Can you see a value? Can you see a value? If you plugged in, we might have like a 0 down here. Yeah, when t equals 0, we're going to have a vertical line right where it starts now. So right when it begins, it has a slope. So let's draw the curve. Let's see what's going on here. By the way, it's just this. Now you don't have to draw the curves of these. You get to skip past all of it, but I wanted to give you the visualization. Right where it starts at t equals 0, you actually have a vertical beginning. Like when your car starts, when you first put your foot on the gas, you are going from 0 to some speed. You're actually increasing. That first instant, you're increasing just so much. And then you're going to kind of slow down. Okay. Blah, 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 blah. So right there, when the denominator is equal to 0, you can think of a vertical line being created. When the numerator is equal to 0, you can think of it being horizontal. Cool. We'll come back with a quick one next time. Kept it under 10 minutes. Next one, shoot. Let's aim for 5 minutes, and we'll do one more problem. All right, see ya.